Hello everyone. We will now begin our lecture on chapter 3.2, which is on logarithmic functions. Now previously we learned about exponential functions, and there is a special relationship between exponential and logarithmic functions. They are the inverses of each other. Now logarithmic functions may be unfamiliar to some of you. However, we are going to start with the basics of logarithms, and we are going to then go deeper into it and then study the relationship between exponential and logarithmic functions. These are some of the topics we are going to cover in this section. We are first going to define what logarithms and logarithmic functions are, and then I said previously that there's a relationship between logarithmic and exponential functions. So we are going to learn how to change from the logarithmic to the exponential form and vice versa. That is, change from exponential to logarithmic form. Then we are going to study how to evaluate logarithms, talk about the properties of basic logarithmic properties, then graph logarithmic functions, talk about the domain of logarithmic functions, and then use common and natural logarithms. Now let's go on to defining what a logarithmic function is. Now it's easier to define logarithms with reference to an exponent. So here we have an exponential form. I'm going to start with the exponential form and convert it to the logarithmic form, explaining the relation between the two. All right. So let me write this down, the exponential form here. It says it's b to the power y equals x. All right. And on this side, on the right hand side, I'm going to use an example like 3 to the power 4 equals 81. Right? So let's analyze this exponential form first. We see there is a b here. This b is referred to as the base. This base is raised to an exponent, which is y. So b to the power y, when we do the evaluation, it will equal to a value which is x. So here's our specific example. In this case, 3 is our base. That base value is raised to an exponent which is 4. So b is 3, y equals 4, and when we evaluate 3 to the power 4, we get a value equal to 81. Right? So this is the exponential form. Let's see how to convert the exponential form to a logarithmic form. So logarithmic form is essentially going to say to what exponent must we raise the base to what exponent should we raise the base to in order to get a value of 81. So in logarithmic functions, your answer is going to be the value of an exponent. The answer is an exponent, right? So how do we transform the exponent form into a logarithmic form? We start with the word log. Okay, so the word log says it's a logarithmic function. So log, and then as a subscript, we put the base. So I'm going to write here below a little bit under the word log, b. It's the subscript. So log base b, and then next to log base b, okay, next to log base b, I'm going to write x. Okay, I'm going to write x and then an equal sign, and then on the other side of the equal sign I'm going to write the exponent variable, which is a y. So remember I just said that the answer from a logarithmic evaluation is an exponent. So the exponent must be on the other side of the equal to sign. All right. So log, the base value goes as a subscript of the word log, and next to log base b we put x, which is the evaluated value of the exponent, and then an equal sign followed by the exponent, the exponent value. All right, so let's convert 3 to the power 4 equals 81 into the logarithmic form. Again, I'm going to start with the word log. All right, now base is 3, right? This 3 is the base. So I'm going to write 3 as a subscript of the word log. And then next to log base 3, I'm going to put that 81. All right, 81. Then the equal sign. And then this exponent here is going to be on the other side of the exponent. So we have log base 3 of 81 is equal to 4. So we could read it as what exponent should we raise the base 3 to in order to get a value of 81, right? And the answer to that is 4, right? So that's the explanation of a logarithmic function, and also an understanding of the relationship between exponents, exponential expression, and a logarithmic expression. Now let's go through this set of example where they show us how to change from logarithmic to the exponential form. Now keep in mind that on the other side of a logarithmic expression, we always have the exponent. So in the first example here, it says 3 equals log base 7 of x. So the other side of the logarithmic expression should be an exponent. So that tells us that 3 is the exponent. So that we know, we have to just find what the base is going to be in order to put it in the exponential form. All right. So the base is whatever the subscript is of the word log, correct? So what we do here is we take the base, which in this case is 7, and we know that the exponent is on the other side of the equal sign. So we are going to make 3 the exponent of the base, which is 7, then the equal sign, and the x is going to go on the other side because x is the evaluated value of the exponential number, exponential expression. All right, so 7 cubed equals x. So x will be a value which is 7 times 7 times 7. Let's work on the next one. Again, we see on the other side of the logarithmic expression, we have a 2 that tells us the 2 is going to be the exponent. Over here, the base b is going to be the base of the exponential form. And we have a 25, which is the evaluated value of the exponential expression. All right, so let's work on it. Again, in the exponential form, we start with the base. So the base is b, so I'm going to write b, and then 2, this 2 is the exponent, equals, and 25 is the evaluated value of b squared. So I'm going to write 25 on the other side. Okay, we do not have to do any calculations here. We just have to put the logarithmic form. We just have to put the logarithmic form to an exponential form. All right. The last one says log base 4 of 26 equals y. Again, the other side, this y, it's on the other side of the logarithmic expression, so that means it's an exponent. So base here is 4 and 26 is going to be the evaluated value from the exponential expression. So when we put it in exponential form, we start with the base 4. This is the exponent y equals 26 goes to the other side of the equation in the exponential form. Okay, so this is how we go about changing from logarithmic to exponential. In the previous example, we learned how to change from the logarithmic form to an exponential form. In this example, they are going to show us how we can change from an exponential to a logarithmic form. All right, so we have 3 examples here and let's go through them one by one. We are given the exponential expression 2 to the power 5 equals x. We have to rewrite this in a logarithmic form. So when we have to do that, always start with the word log. So we start with the word log and then as a subscript of log, put the base value from the exponential form. So the base value here is a 2. So log base 2, and then next to log base 2, we put the evaluated value of the exponential expression. So I'm going to put log base 2 of x, then the equal sign, and on the other side of the equal sign is going to be the exponent. Keep in mind that a logarithmic expression always evaluates to an exponent. The answer from a logarithmic expression is an exponent. So the exponent of our exponential form is 5. So we write 5 on the other side of the equal sign. Let's work on the next one. It's b cubed equals 27. So again, start with log and then put the base of the exponent as a subscript of log, in this case b, and then the evaluated value from the exponential is 27, so I'm going to put 27, then the equal sign followed by the exponent, which in this case is a 3. The last one is e raised to the power y equals 33. Now recall that e is a natural base in an exponent or of an exponent. E is a natural base, it's an irrational number, E is a constant value, it's not a variable, it's a constant value, and it has a value of 2.72 rounded to the second decimal place, but it has a lot more decimal values or decimal places to it. All right, so e to the power y, again start with the letter with the word log, and e is the base of the exponent, so I'm going to write e as a subscript of the log, and then 33 comes after log base e. So log base e of 33 equal sign followed by the exponent, which in this case is a y. All right, so that completes our changing from the exponential to the logarithmic form in these given examples. Now, one thing I just want to give you a preview of is that in some of the later slides, we will revisit log base e, and log base e has a special notation. It's referred to, or it's going to be written as ln. ln is natural logarithm. So whenever we have a log of the base e, log base e, it's going to be replaced by ln. All right, natural logarithm. So in the future, whenever you see ln appearing, please in your mind interpret it as log base e. But we are going to talk about that in more depth in some of the future slides. We are now going to learn how to evaluate logarithms. Now keep in mind that the outcome of the evaluation from a logarithm is an exponent. The answer that we are looking for here is going to be the value of an exponent. So we have two examples here. One says log base 10 of 100 and the other one says log base 5 of 1 divided by 125. So the best thing to do here is first convert this logarithmic form to the exponential form. It'll be easier for us to understand what we are looking for. All right. So we see here the subscript of log is a 10. So that will represent the base of the exponent 10. And then this value 100 is going to be the evaluation from the exponential expression. So this 100 goes to the right hand side of the equal sign. So I have the equal and I'm going to put 100, this 100 on the other side of the equation. Okay, so what we are looking for here is an exponent of 10. Again, the answer from a logarithmic evaluation is always an exponent. So we put this here into an exponent form. 10 to the power of what value is equal to 100. All right. So we have to fill in this box here, and that is going to be the answer of this logarithmic expression. So we know 10 to the power 2 gives us 100. So the answer is a 2. Okay. So we put a 2 inside the box. So the solution for part A says log base 10 of 100 means 10 to what power gives 100. So log base 10 of 100 is a 2 because 10 squared equals 100. Got it? Part B says log base 5 of 1 over 125. We'll follow the same process. We will try to put it in exponent form with 5 as the base. So I'm going to take the 5, okay, and then see to what power, to what exponent we must raise it to get an answer of 1 divided by 125. 1 divided by 125. So we know 5 times 5 times 5 is 125. 5 cube is 125. All right. So 5 cube is 125. However, this question here is 1 divided by 125. All right. The 125 is in the denominator. Now going back to the rules of exponent, all right, negative exponents means reciprocal. All right, so if 5 cube is 125, then 5 to the negative 3 is going to be 1 divided by 125. So if we put a minus 3 inside the box here, okay, minus 3 inside the box, then it is going to be equal to 1 divided by 125. So here we not only found the exponent, but we also used the rule that negative exponents means reciprocal. All right, 125 will become 1 over 125 when the exponent is negative. So let's read what solution they have put here. It says log base 5 of 1 over 125 means 5 to what power, to what exponent gives 1 over 125? So log base 5 of 1 over 125 is negative third, because 5 raised to negative third equals 125. So the answer of this evaluation of this entire expression here is going to be negative 3. Okay, I'm going to box this so it's separate from the actual problem here. So your final answer is going to look like this. All right, log base 5 of 1 over 125 equals negative 3. Here is another example of evaluating logarithms. We are going to use the same process but apply a different exponential rule. All right, so the first step is to convert this logarithmic expression to an exponential expression. So here what we have, the base is 36, right? So I'm going to write 36 as the base of the exponent and then put a box above 36, which is going to hold the exponent, and then on the other side of the equation I'm going to put this 6. All right, so 36 raised to what exponent gives us a 6, right? So here we have to apply the rule of fractional exponent. If you recall, all right, 36, we can see here easily the square root. The square root of 36 we know is going to give us a 6. Now, the square root can be transformed to an exponent, correct? This is 2, correct? Square root means the root is 2. To convert it to an exponent, what do? We write it as 1/2. So fractional exponent can be converted to radical expression, whether square root or cube root or any other radical roots, right? So 36 to the power half equals 6. So if we take the square root of 36, which is the same as 36 raised to the power half, we will get an answer of 6. So the answer from evaluating log base 36 of 6 is going to be 1/2. All right, and that's what they have here in the solutions as well. It says log base 36 of 6. Let me take out the pointer here. Log base 36 of 6 means 36 to what power gives 6? Log base 36 of 6 is 1/2 because 36 raised to the power half equals 6. So here not only you are using your the process to convert a logarithmic to an exponent, but to find the exponent you are applying the rules of exponential expressions. Now we are getting into some examples which look a little more complicated than the previous ones, but if we follow the same process and apply the rules of exponents, we'll see it's not as hard. So here it says evaluate log base 3 of the 7th root of 3. So we're going to start with converting this into an exponent form first. All right, so here we have the base 3. I'm going to write 3 as the base of the exponent, and then I'm going to put a placeholder here for the exponent, because after all we are trying to find an exponent as a result of this evaluation of the logarithm, right? So 3 to the power of what value is equal to the 7th root of 3. Now in the next step, I'm going to further break down that 7th root of 3 on the right hand side. So I'll still keep the left hand side as is, 3 raised to a certain exponent. But on the other side of the equation, I'm going to transform the 7th root of 3 and write it in exponent form. So 7th root of 3 is equal to 3, or rather is the same as 3 raised to the power 1/7, right? 1 divided by 7 is the exponent. So if the right hand side, if the right hand side has an exponent 1/7, all right, then the left hand side, which also has a 3, must be the same exponent because it's equal, right? This side is equal to this side. We have a 3 for the base on the left hand side. We have a 3 for the base of the right hand side. If they are equal, then this exponent on the left hand side must also be 1/7, right? So I'm going to fill this box and write 1/7 as the exponent. So our final answer of this evaluation is that log base 3 of the 7th root of 3 is 1 divided by 7. All right. We are now going to learn about a couple of logarithmic properties involving 1, because these two properties are going to be the same for any logarithmic expression involving 1 of this form. So we have here log base b of b. Whenever the subscript of a log and the value next to it are the same, the answer, the evaluated value, is going to be a 1. Okay, that is going to always be the case no matter what the value of b is. So let me run through an example. I'm going to dig out my pen here, and I'm going to use a specific example here. Let's say log base 4 of 4. All right. So I'm going to first convert this to an exponential form. So the subscripted value 4 becomes the base of the exponent raised to what exponent is going to give us this value next to log base 4 equals 4, always going to be 1, correct? If we try another one, log base 25 of 25, okay, it's same process, 25 raised to what power is going to give us 25? 1. So this evaluation is going to equal 1 for an answer. Okay, so that's rule 1. Whenever the base of the log, the subscript of the log, and the value next to it are the same, just blindfoldedly know that the answer is going to be a 1. B to the power 1 is going to be a B. The next one says log base b of 1 equals 0. All right. It tells us b raised to what power is going to give us a 1. Any number raised to the power 0 is a 1 always, right? So if we have, let me take out my pen again, log base 5 of 1 equals what number? All right. Evaluates to what? Let's see. Let's change this to exponent form. 5 raised to what power is going to give us a 1? 0, right? 0. An exponent of 0 gives us an answer of 1 no matter what the base value is. All right, so the logarithmic answer, or the logarithm of base b of 1 is always going to be equal to 0 no matter what b is. Let's go through these two examples using the properties that we just learned before. It says log base 9 of 9. What is the answer going to be? Again, here we see that the subscript of the log and the number next to it are the same. All right, whether it's 9 or 10 or 20 or no matter what the values are, as long as the subscripted value and the number next to it are the same, then we know that the answer is going to be 1, because 9 raised to the power 1 will give us a 9. So the answer in this case is a 1. So because log base b of b equals 1, and we see that here the subscripted value is a 9 as well as the value next to it is a 9, our answer will be equal to 1. The part B says log base 8 of 1. So whenever we have a 1 next to log base b, the answer is going to be a 0 no matter what this subscripted value is, whether it's 8 or 100 or 2000. As long as the number next to it is a 1, it'll always be an exponent of 0. So because log base b of 1 equal to 0, by that property we learned before, we conclude log base 8 of 1 equals 0. Now let's talk about the inverse properties of logarithms, which is quite an important property of logarithmic functions. All right, here it says log base b of b to the power x equals x. So when we have a subscript of b and next to it we have an exponential value where the base is the same as the subscript. So we see a b here. This b to the power x is an exponential expression, right? This is an exponent here. So the base of the exponent is a b and the subscript of the log is also a b, right? When that is the case, then the answer, the evaluated result, will always be equal to whatever this exponent is. All right, so let's again work through an example with numbers. So I'm going to first convert this. To exponent form. So we have log base b of b to the power x. What does this say? This is saying that b raised to what exponent is going to give us b to the power x? What exponent will give us b to the power x? And we did one example, I think 2 or 3 slides back, a similar example. All right, we have the same base here. All right, we have an equal sign. If the right hand side of the equation has an exponent of x, then because this is an equality, the left hand side must also be the same exponent, because both the bases are the same, right? And that's exactly what they say here. Log base b of b to the power x equals x. The inverse of that is b, and I'm pulling up my pointer here, b raised to the power log base b of x equals x. All right, so this is an exponential form. This is not a logarithmic form, or even though the exponent is given to us in logarithmic form, but it's essentially an exponent. We don't see a log word here on the left hand side of this b. Okay, so I'm going to rewrite this expression in logarithmic form. Okay, so, and we will get this expression here, this expression. So let's follow the process to convert an exponent to a logarithm. Start with the word log. All right, and the base is a b, So I'm going to put that as a subscript of log, and then this expression x, all right, this expression x is going to be put here, all right. And then on the other side, we are going to have log base b of x, okay, which are equal, right? Log base b of x is equal to log base b of x. Okay, so that's the inverse properties of logarithm. Let's quickly run through the two examples of using inverse properties of logarithms here. We are first given log base 7 of 7 to the power 8. We first observe that the subscript value of the log is a 7, and the base of this exponential form is also a 7. Now, as long as these two are the same, then the answer is going to be whatever the exponent of 7 is. So here in this case, the answer is going to be 8. All right, because the subscripted number and the uh, base of this entire exponential expression are the same, the evaluated logarithmic value is going to be whatever this exponent is, 8. All right. So let's read what the solution they've given here. It says because log base b of b to the power x equals x, we conclude that log base 7 of 7 to the power 8 equals 8. The other one is applying the second inverse property we learned. So this is an exponential expression, right? 3 to the power log base 3 of 17. What the rule told us was as long as the base of the exponent here and the subscript of the log in the exponent are the same, then the answer is evaluated answer of this exponent is going to be whatever this value is next to log base 3, which is 17. So the answer is because b of log base b of x equals x, by the property we learned, we conclude that 3 of log base 3 of 17 is also going to be 17, which is whatever number is next to the log base 3 and the exponent of 3 to the power log base 3 of 17. Now we learn about graphing of exponential and logarithmic functions. Now, before we go into the actual graphing, let's recall that exponential and logarithmic functions are really inverses of each other. When we were studying inverse functions, we were told of two properties for inverse functions in particular. One is that the domain of a function becomes the range of the inverse function, and the range of the function becomes the domain of the inverse function. So if we have f of x, all right, so if we have f of x with its domain and range, and there is inverse f of x, right? What will happen is the domain of the regular function will become the range of the inverse function, and the range of the regular function will become the domain of the inverse function. In other words, the x and y coordinates will flip in the inverse function. The x and y coordinates of the regular function will flip in the inverse function. And the other thing is that the graph of the inverse functions will be a reflection will be, or let's say it'll be symmetrical. Okay, it'll be symmetrical or a reflection across the line, symmetrical across the line y equals x. All right, so these are the two properties that we had learned of any inverse function, not just exponential and logarithmic. It applies to any inverse function. Now let's see what we have here about graphs. It says here we have two graphs. One is an exponential function and the other one is a logarithmic function, right? And this logarithmic function is derived from the exponential function 3 to the power x. So 3 to the power x is the exponential function, and log base 3 of x is obtained from the exponential function, and that will be our logarithmic function. And we want to graph them in the same rectangular plane. So we first set up a table for the exponential function, plug in a few values of x into this function here, 3 to the power x, and find the corresponding y values. And then all we do is, for the logarithmic function, we'll flip the x and y coordinates, and then we'll first plot the exponential graph and then we'll plot the logarithmic graph. As simple as that. Let's continue with the graphing of the two exponential and logarithmic functions that were given to us. One of them is f of x equals 3 to the power x, and the other one is g of x equals log base 3 of x. Now we know that these are the inverses of each other. We started with the exponential function. We picked some values for x and ran them through the exponential function and came up with the y coordinates, the y values. All right. Now I'm going to put all these x and y coordinates in ordered pairs here. So let me do that. I'm going to write here f of x. So the first ordered pair is -2, 1/9, and then we have -1, 1/3, then we have 0, 1, and finally we have 1, 3. All right. So these are the ordered pairs of the exponential function. Now we have to come up with the ordered pairs of the logarithmic function, which is g of x. Now, if we know that they are inverses of each other, and we also know the special property of inverse function, that is, the domain of the function becomes the range of the inverse function, and the range of the function becomes the domain of the inverse function, then all we need to do is flip the x and y coordinates for the logarithmic function. All right, just take the x and y coordinates of f of x and flip them, switch them, and that will be the ordered pair of the logarithmic, the inverse function. So let's do that. I'm just going to take the 1/9 is now going to be this 1/9, which is the range, which is the y value of the exponential function, becomes the domain or the x value of the logarithmic function. So 1/9 comma -2 is one ordered pair for the for g of x. Next one will be 1/3 comma -1, and then 1 comma 0 and 3 comma 1. So you see what we did? We just flipped the x and y coordinates and made them the ordered pairs of the logarithmic function. And then once you have the ordered pairs, all you need to do is plot them on the same coordinate system and connect the points and you get your graph. Okay, that's all there is to it. Now, here they have, of course, done the calculation. All right, they have shown the calculation how they got the y values for the logarithmic function. So when x is 1/9, it's -2. When x is 1/3, when we run it through the log base 3 of 1/3, we get -1. Log base 3 of 1 is 0, and log base 3 of 3 is a 1. All right, so we got the same ordered pairs as we wrote here. All right, 1, 9, -2, 1/3, -1, 1, 0, and 3, 1. So now that we have the ordered pairs for both the exponential and logarithmic function, let's just graph them on the same rectangular plane. Finally, we see the two graphs drawn on the same coordinate plane here. The blue graph here is that of the exponential function f of x equals 3 to the power x, and the red graph here is that of the logarithmic function. And we see that the two graphs are reflected. They are reflections of each other across the line y equals x, as should be with the case of inverse function. Let's look at the points on the exponential graph. These are the points that we had found as ordered pairs previously. When x was -2, y was 1/9. So this point is just slightly above the x-axis. The next point was -1, 1/3. So at -1, we have this point just 1/3 way between 0 and 1 of the y-axis. When x was 0, y was 1, and when x is 1, y was equal to 3. So we have the 4 points and we connect them and we get this graph of the exponential function. Now, as we had learned when we were doing exponential graphs, that to the right side of the graph rises indefinitely to infinity, and as the x values decrease, the graph heads closer and closer towards the x-axis, which is the line of y equal to 0, but it doesn't touch the x-axis. So the exponential graph does not have an x-intercept. The exponential function and graph does not have x-intercepts. Now let's look at the logarithmic graph here, the red one here. When x was 1/9, y was -2. So we have a point here. Then when x was 1/3, y was -1. All right, again, remember that we obtained the ordered pairs by flipping the coordinates of the exponential function. We got this point here when x is 1/3, y is -1. When x is 1, y is equal to 0. So we got a point on the x-axis, which is the x-intercept of the logarithmic graph. And finally, when x was 3, y equals 1, we connected the points and we got this graph. Now let's make some observations of the logarithmic graph here. We see there is an x-intercept. The exponential function never had an x-intercept, but the logarithmic graph has an x-intercept. Now, as the x values increase, the graph rises, not as fast as the exponential graph, but the y values keep increasing. When x values are between 0 and 1, the graph drops. The y values decrease all the way down to -infinity. However, the x value never goes beyond 0. In fact, it is never 0 either. All right, so the graph, as you see, is heading closer and closer towards 0. All right, but towards x equal to 0, but it will not touch or cross the it will not touch or cross the y-axis. So it will not have a y-intercept. All right, it will not have a y-intercept. However, the y values decrease all the way to negative infinity. Now that we've made some observations of the graph of logarithmic functions, let's put together some characteristics of logarithmic functions as well as that of their graph. All right. First, we talk about the domain. The domain of a logarithmic function consists of all positive real numbers starting immediately after 0 all the way to positive infinity. So note we have a round bracket before the 0. So that means that 0 is not included in the domain of a logarithmic function. But any value greater than 0 all the way up to infinity is in the domain of the function. The range of f of x of the logarithmic function consists of all real numbers negative infinity to positive infinity. So there is no restraints, no constraints on the range of the logarithmic function, but for the domain it's 0 comma infinity, so all values greater than 0. Number 2, the graphs of all logarithmic functions pass through the point 1 comma 0. That means the graph has an x-intercept at 1, x equals 1. All right, so that's the x-intercept. The x-intercept is 1, but there is no y-intercept. If you remember, the graph was dropping all the way to infinity at x equal to 0, but it was not touching the y-axis. If b is greater than 1, all right, if b is greater than 1, then the graph goes up to the right and is an increasing function. So if this b is a value greater than 1, then the graph goes up to the right and is an increasing function. The y values increase. If b is a value between 0 and 1, that means if it is a fractional value between 0 and 1, the graph goes down to the right. All right, it goes down to the right and is a decreasing function. And then number 5 says the graph of the logarithmic function approaches but does not touch the y-axis. The y-axis, or x equal to 0, is a vertical asymptote. Okay, so these are the characteristics of logarithmic functions that we can obtain from the behavior of the graph. Now I'm going to go rather quickly through this slide, which talks about the domain of logarithmic functions, because we already discussed the domain when we were talking about its characteristics, right? Now it says here that the domain of a logarithmic function can be found by making the function greater than 0 and solving for x. We saw that the domain of a logarithmic function starts from 0, but it does not include 0. So we had round brackets to the left of 0 and then comma infinity. So 0 is not included in the domain, but anything greater than 0 can be a part of the domain, right? So when we are asked to find the domain of such a function, then what we do is we take the function g of x or f of x, whatever it may be denoted as. So we take g of x and make it greater than 0 and solve for x, and then accordingly include those x values into the domain. This is an example of finding the domain of a logarithmic function for a specific given function. So it says find the domain of f of x equals log base 4 of x minus 5. So to find the domain, all you do is take this x minus 5, make it greater than 0 and solve for x. So when we solve x minus 5 greater than 0, we get x greater than 5. Bring the minus 5 over to the other side, so it becomes 0 plus 5. So x greater than 5. So that means the domain is going to be all values greater than 5, written in interval notation. That's going to be starting with a round bracket around 5. So 5 comma infinity. All right, so we have to make sure that this x minus 5 evaluates to a value greater than 0, and then state the domain accordingly. This is a graphical representation of the domain value of the domain of x greater than 5. You see what happened is earlier, okay, with the basic logarithmic graph, okay, when it's log base 4 of x, then the graph had a vertical asymptote at x equal to 0, right? When it's log base 4 x minus 5, then it shifts 5 units to the right, and now the vertical asymptote is at x equals 5. So you should also be able to relate this to the transformation of graphs, right? You see, this x minus 5 is of the form x minus h, all right? X minus h. Remember, that was the form of horizontal shifting. Or if we put x minus 5 and align it with the x minus h form, we get x minus 5, right? And that 5 is positive, h is positive, therefore it would mean, it would imply 5 units shift to the right from its original position of the base graph. And that's exactly what happened. The vertical asymptote has shifted from 0 to 5, and the graph now is aligned to a vertical asymptote of x equal to 5. All right. So it says here as a solution, we found that the domain is of f is 5 comma infinity, with 5 not being included in the domain, and that is what is illustrated in the graph. All right. It's just that the graph has shifted 5 units to the right, which also agrees with the transformation rules that we had learned before. In the next few slides, we are going to talk about two special logarithms. One is called common logarithms and the other one is called natural logarithms. So we'll start with the common logarithms. This kind of logarithms has a base of 10. So whenever we see something of log base 10 of x, we do not write the subscripted value, the base. All right, we don't need to write the 10. We just write it as log of x. So when you don't see a subscript next to log or a subscript of log, assume that it is log base 10. Just know it is log base 10. This is something we have to know, we have to remember. So when we see a subscript missing, that means the base, the subscript is 10. Okay, so the logarithmic function with base 10 is called the common logarithmic function and is expressed as log of x. So it does not have a subscript. When you see one missing, then assume that it has base 10. Now here's an application problem with common logarithms. So here it says the percentage of adult height attained by a boy who is x years old can be modeled by f of x equals 29 plus 48.8 times log of x plus 1, where x represents the boy's age from 5 to 15 and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So here a function is given, a logarithmic function is given. X will be a boy's age, but it will be between the age of 5 and 15. So here you see the domain is restricted between 5 and 15 inclusive. The f of x is the percentage of his adult height. So, what percentage of the adult height he has reached at a certain age. So, this is a straightforward problem. All you need to do is plug in a value for x and calculate this and you will get f of x. So what is the x that we have to plug in here? It says approximately what percentage of his adult height has a boy attained at age 10? So age is 10, therefore x represents age, so x is going to be 10. That's why they have f of 10 here. They've plugged in 10 into x. So we have log of 10 plus 1, and then once we do that, just evaluate. You will need to use a calculator to do this calculation, and we come up with an approximate percentage value of 80%. So a 10-year-old boy has attained approximately 80% of his adult height. Now let's see how the properties of common logarithms compare with those of general logarithms, where the base can be any value. All right. So the first one here says log base b of 1 equal to 0. So over here we see that the base is referred to as b. It is a visible base. In common logarithms, the base is not visible, but that means we have to assume that the base is a 10, right? That's the base for common logarithms. Now, if we translate this into an exponent form, then what does it mean? It means b raised to the power 0 is equal to 1. Now, any value raised to the power 0 will always be equal to 1. All right, whether it is any generic number represented by b, or whether it's 10, or whether it's e, which is the natural base. Any number raised to the power 0 will always be a 1, and that is true with the case of common logarithms as well. So log base b of 1 equal to 0. With common logarithms, we write log of 1 equal to 0. In number 2, we have log base b of b equal to 0. That means in exponential terms, b raised to the power 1 is b. That means any number raised to the power 1 will be that same base value, correct? So log base b of b, as long as the subscripted value and the number next to log are the same, the resulting answer will always be a 1. In the case of common logarithms, log of 10 equals 1. All right, so this number next to log has to be a 10. Why? Because the log has a base of 10. So log of 10 is equal to 1. 3 and 4 are two inverse properties. That means log base b of b to the power x equals x. So as long as the base of the log and the base of this exponent next to log base b are the same, the answer is going to be this exponent value, whatever that is. So log base b of b to the power x equals x. In the case of common logarithms, it's log 10 to the power x equals x. All right. The base of the logarithm and the base of this exponential expression have to be the same. 10, 10 equals x. And then finally, this you may recognize is really an exponential expression. However, the exponent itself has the logarithm in it. So b to the power log base b of x equals x. So this being an exponent, this being an exponential expression, as long as the base of the exponent as well as that of the logarithms are the same, the resulting answer will be whatever we have next to log base b in the exponent is going to be x. In the case of common logarithms, it's going to be 10 raised to the power log of x equals x. So we have a 10 in the base, and although again we do not see the base of the log, that means it is a 10. We can safely assume it's a 10. And therefore, the answer is whatever is next to the log, right? Natural logarithms have a base e and they are called the natural logarithmic functions. Now keep in mind that e is a number. E is a constant value. It is an irrational number with an interminable set of decimal places. However, we can round it up to the second decimal place as 2.72. The notation for natural logarithms is ln of x. That means the natural logarithm, n for natural logarithm of x, and that translates to log base e of x. So the base is an e. So whenever you see an expression as ln of x, just know that it means logarithm whose base is an e, ln of x. Let's see here how the properties of natural logarithms compare with the general properties this time. So we have log base b of 1 equal to 0. In the case of natural logarithms, it's going to be ln of 1 equal to 0. Now that stands true for any base, all right, whether it is base b or base 10 or whether it's base e. Ln of 1 will be a 0. Log of 1 will be a 0. Log base b of 1 will always be a 0. Number 2 says log base b of b equals 1. So that means when the base of the logarithm and the number next to it or the variable next to it is are the same, then the resulting answer will be a 1. In the case of natural logarithms, ln of e is always equal to 1. Okay, so ln means log base e of e equal to 1, correct? For number 3, it's log base b of b to the power x equals x. In the case of natural logarithms, it's ln of e to the power x will be equal to x. Likewise, for this exponential expression where the exponent itself is a logarithm, this is the case where we have b as the base. In the case of natural logarithms, it's e raised to the power ln of x. Again, we are going to read ln of x as e to the power log base e of x. So this e and the base of ln are the same. When that happens, the resulting answer is an x, whatever value is next to ln here. Let's end this with an application problem with natural logarithms. It says when the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times ln of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. So here x represents the number of minutes and f of x represents the temperature increase, the temperature in other words, in Fahrenheit. Use the function to find the temperature increase to the nearest degree after 30 minutes. So we are just going to plug in 30 into x and uh, calculate this, and we will come up with the corresponding temperature. So that's what they've done here in the solutions. They've plugged in 30 into x and evaluated this expression. So 13.4 times ln of 30 minus 11.6 is approximately 34. You have to use your calculator to do this calculation. So it says the temperature will increase by approximately 34 degrees after 30 minutes.